Resistivity is a physical characteristic of a material. Different materials have different resistivities, and thus they have different resistances to the flow of electricity. The purpose of this lab is to determine the resistivity of copper. And to do that, we're going to use this piece of equipment, which has an assortment of different copper coils. And we're going to focus on these two right here. And these copper coils, when I pass electricity through them, I'll supply a voltage. A current will flow through the copper, but the copper has resistance to the flow of that current. And the amount of resistance is a function of how long the wire is and its diameter. So we'll systematically vary the voltage that's flowing through these copper coils, and at different voltages we'll measure the resulting current. And then we'll be able to use Ohm's law to calculate the resistance of the copper coil. And then knowing how long the wire is and knowing its diameter, we'll be able to use the wire equation to calculate the resistivity. Okay, so the first step is to set these coils up in a circuit with a power supply to supply voltage, and two digital multimeters, one set up as an ammeter to measure current that flows through the coil, and the other set up as a voltmeter to measure the voltage drop across the coil. Then we'll have voltage, we'll have current, we'll be able to do we'll do linear regression to figure out resistance. And once we have resistance, you'll be able to calculate resistivity. All right, so let's do this. Okay, so here's the setup. I got a power supply over here supplying a voltage, a DC voltage, to, right now I'm hooked up to this coil right here, and so current will flow out of the power supply through this coil of wire and back to the power supply. And I know it's hard to follow the circuit with this jumble of wires right here. And I have two multimeters. This one's going to be turned on to measure voltage. Right now the voltage is 0 because the power supply isn't supplying any voltage. And this one, and of course it's a voltmeter, so it's set up in parallel. The voltmeter is attached to these two leads, so it's measuring the voltage across this coil. This voltmeter is set up to measure current, and so it's in series with the rest of the circuit. Alright, so we need to take some measurements and record them. Okay, so you need to record these as well. Alright. Okay. So at 0.229 volts, we have a current of 0.43 amps. So let's write that down. So I'll make a little table. Volt and current. So at 0.228 volts, the current is 0.42 amps. That's amps. This is volts. All right. All right, at 0.3 to 0 volts, the voltage is 0, the current is 0.6 amps. Okay, so for this first wire, it's made of copper. Cu is the abbreviation for copper on the periodic table. It was 10 meters long, and 22 was its wire gauge. AWG is American wire gauge. So if I know that, I can look up in a table what its diameter is. I supply that for you in the lab write-up this week. So what we did then is for this wire, we systematically varied the voltage and measured that voltage and the corresponding current that it resulted in. So we have a data table of this data, and here it is. So at 0.228 volts, the current in amperes was 0.42. At 0.320 volts, the current was 0.60 amps. At 0.430 volts, the current was 0.81 amps. At 0.533 volts, the current was 0.99. At 0.606 volts, the current was 1.13 amps. At 0.743 volts, the current was 1.36 amps. Okay, so now I'm going to redo this with a different copper coil. All right. All right, so back to our table here, and so now I have some data for a second coil, and it is also copper, and it's also 10 meters, but this is 28 gauge. That means it has a smaller diameter. But I repeated the experiment. I systematically varied voltage and measured the resulting current in amperes. All right, so I took a lot of data points. At 0.219 volts, the current was 0.10. At 0.613 volts, the current was 0.27. At 0.952 volts, the current was 0.42. At 1.86 volts, the current was 0.82. At 2.62 volts, the current was 1.10 amps, and at 3.04 volts, the current was 1.30 amps. Okay, so I have data for the 10 meter 22 gauge wire and data for the 10 meter 28 gauge wire, and this is what it looks like. All right, so what's the next steps? How are we going to use this data to calculate the resistance of each of these coils, and then use its physical properties to calculate resistivity? All right, so let's talk about how we're going to analyze this data. All right. So first, let's review the schematic of this circuit. So there's a power supply. That's the schematic symbol for a power supply. And it's connected to this coil of wire, which serves as a resistor. That's the schematic symbol for a resistor. And then this is hooked up to one of my multimeters, which is functioning as an ammeter, and it's in series with the resistor. And then I have another multimeter that's hooked up in parallel to the coil of wire as a voltmeter. So that's a schematic of what this circuit looks like. So the voltmeter is always hooked up in parallel. It measures the voltage drop across the resistor. And the ammeter is always hooked up in series. It measures the current that flows through the circuit. All right, so going to use our data to figure out the resistance of our coil of wire, our resistor. Well, as is customary in physics lab, I'm going to want you to do linear regression on your data. You might say, well, Ohm's law is V equals I times R. So if I just take my V's, my voltages, and plug in the corresponding currents, I could solve for resistance. And I could calculate a bunch of resistances and average them together for all my data. But let's do something more sophisticated. All right, what you're going to do is you're going to plot. And in this experiment, the thing that we're controlling is the voltage. So that would be the independent variable, and then the dependent variable is current in amps. So you have these data points. You have these data points that you can plot, and then if you fit the data with a line of best fit, the slope of that line of best fit is related to the resistance. Can you figure it out? Do you see the relationship? Well, to see this more clearly, let's do this. Let's take Ohm's law and rearrange it. Just solve for I. I equals 1 over R times V. So if I plot I on the y-axis and V on the x-axis, I expect the slope of the relationship to be equal to 1 over R. Therefore, R equals 1 divided by the slope. All right. So if you plot your data in Excel and use the linest function, or apply a trend line to your plot, you'll be able to figure out the slope of this relationship. And once you know the slope of the relationship, you'll be able to calculate resistance. Okay. So you're going to do that. Remember, you keep track of your the standard error of the slope. You'll use that as an estimate of the uncertainty. All right, then what's next? Okay, once you have resistance, you're going to use that to find rho, which is resistivity, and that's a property of copper. And what's the relationship? Well, there's an equation called the wire equation. The resistance of a wire is equal to the length of the wire times resistivity divided by the cross-sectional area. So we know the lengths of our wires, 10 meters in both cases. What about cross-sectional area? Well, we can use the wire gauge for that. So in the handout, I give you the wire gauge, and from the gauge you can figure out the diameter, and of course diameter is 2 times the radius, or in other words, radius is diameter divided by 2. And once you have the radius, you can figure out the cross-sectional area of the wire, that's A, and the cross-sectional area of the wire, it's a circle, so the cross-sectional area would be pi r squared. All right, just be careful. When you do this calculation, you got to be careful with units. Make sure your diameter is in units of meters, so your cross-sectional area is in units of meters squared. It's going to be a very, very small number. But you got to do that so that if you plug in length in meters and resistance in ohms and cross-sectional area in meters squared, you'll get resistivity in SI units, which is the goal here. If we rearrange this, resistivity then is R times the cross-sectional area divided by L. All right, so that's an outline of the data analysis you're going to do, and there's a so you'll make your you'll take your data, the data that we collected here together, you'll plot it in Excel, you'll do the linear regression analysis in Excel, and then use the results of that to calculate the resistance for each of the coils. There's 2 of them, so you'll do this twice. And then once you have resistance, you'll calculate resistivity and then compare that to the expected value of resistivity for copper, which is supplied in the lab handout materials. So I want to talk a little bit more about the data analysis, give you a little extra help on the data analysis. In particular, I want to talk about how do you deal with propagation of error in this experiment. All right, so the main result you get from the linear regression, the line of best fit, is you're going to get a slope. And as we just talked about, the slope is equal to 1 over resistance. Why? Because you plotted I as a function of V. And Ohm's law can be written as I equals 1 over R times V. Okay, so this is the main result of this experiment, is you're able to get the slope of a line of best fit, and that's equal to 1 over the resistance of your copper wire coils. All right, and then the next step was, well, once you know R, you can calculate resistivity. Resistance times cross-sectional area divided by length equals resistivity. And that follows directly from the wire equation that we just talked about. All right, so what about the uncertainties? Well, when you calculate the slope of a line of best fit, you got this data and you fit it with a line of best fit, you're going to get the slope, if you use the lin-est function in Excel, what you get, the return from this function is you get the slope, but then you also get the a measure of the standard error of the slope. So we use the standard error of the slope as our estimate of uncertainty, or error in our slope. So when you report that, if you were just reporting that, it would be reported as slope plus or minus the standard error of the slope. Well, in this case, the slope isn't the end game. That's just, we can use the slope to find resistance, and the relationship is up here, right? So if we follow this through to the end, we get R equals 1 over the slope. So where does that leave us with the uncertainty of R? Well, here we have a calculated quantity. R is calculated from the slope. It's equal to 1 over the slope. And the rule for error propagation that we're using in this class is that when you do division, the error in the result of that division is the same as the sums of the fractional uncertainties of the numerator and the denominator. And here this is really easy because the numerator is a constant. It doesn't have any uncertainty. You're going to treat it as a constant. So what I'm saying here is the uncertainty of our resistance in fractional terms, sigma over R, is going to be equal to the uncertainty of our slope in fractional terms. And we're using the standard error in the slope that we get from the lin-est function as our estimate for sigma slope. So the uncertainty in R is going to equal, if we just solve for that, R times the fractional uncertainty of the slope. All right. There's a handout on Sakai that summarizes these rules for error propagation, if you want to review them. Okay, well then, what about rho? So rho is calculated from R. Rho equals R times A over L, cross-sectional area divided by length. So here we have a situation where we're calculating rho from another value, R, resistance, that has uncertainty associated with it. But to calculate this thing, we're just multiplying by a constant. We'll treat A and L as a constant with no uncertainty, no error whatsoever. And the rule for error propagation, when you're just multiplying by a constant, is then the uncertainty in rho is going to equal the uncertainty in the resistance multiplied by the same constant. In other words, in absolute terms, the uncertainty just scales by the same constant. All right, so once you find sigma r from this relationship right here, you'll be able to find sigma rho. All right, one more thing. What about percent error? So this is what I want you to do in the last part of this. The last thing I want you to calculate is the percent error between your experimental value for rho and the actual accepted value for rho. And that's how you do it. You take the absolute value of the difference between your experimental value and the accepted value, or actual value, divide by the actual or accepted, multiply by 100. You get percentage terms. All right, so I hope you find this last little piece helpful in figuring out these last pieces. So let me just finish up with a few suggestions on being careful and being correct. First, units. Be careful with units. If I can spell units. Units. So the diameters I give you in the lab handout are in units of millimeters. So make sure you divide by 1,000 to convert those measurements to meters. And of course that's diameter, so divide by 2 to get radius. All right? So be careful with your units. What else? That's the main thing. Now, as far as precision, how many decimal places should you enter your answers? There's a WebAssign assignment posted for you to enter your data in your calculations, and as is customary, WebAssign doesn't necessarily go by what best practices are in terms of number of significant digits. So just as a general rule, make sure you add a few extra decimal places to your numbers so that WebAssign has sufficient information to check whether or not the values you're entering are correctly calculated or not. All right, so the WebAssign assignment's posted, this video is posted, the text of this lab activity is posted. So good luck, and shoot me an email if you're having any trouble.